Welcome to Chapter 11, Fireground Operations. It is the driver-operator's responsibility to secure a water source upon arrival on the incident scene. Fire hose evolutions are critical to the success of firefighting operation. Hose evolutions are divided into supply line operations and attack line operations. Once arriving on the scene, and prior to exiting the cab of the fire apparatus, there are several steps that the driver-operator needs to complete. Once the pump is engaged, upon exiting the cab of the fire apparatus, the driver-operator has other responsibilities. Before leaving the fire station to respond to the scene, the driver-operator should have a working knowledge of water sources at or close to the scene. This can be accomplished by using a map book with hydrant locations in it and by becoming familiar with water sources within the response area, including lakes, ponds, canals, and drafting hydrants. Another water supply evolution is furnishing water to a standpipe or sprinkler system. Fire department connections on buildings are provided so that the fire department can pump water into standpipe and or sprinkler systems. When your crew first arrives at the scene, you may initially need to supply attack lines from your onboard tank, but then have a supply line laid to your pump from another fire apparatus, or via a hand-laid supply line. It is important to establish a supply line early and then perform a changeover operation. The driver-operator has additional duties and responsibilities on the scene. Once the pumping operation is underway, the driver-operator must monitor specific gauges on the pump panel to ensure that an adequate supply of water or foam is available for the duration of the incident. Learning objectives. By the end of this chapter, you should be able to describe securing a water source after arriving on scene, describe the driver-operator's responsibilities with proper hose layouts, describe cab procedures when positioning the fire apparatus at the fire ground, describe the driver-operator's responsibilities prior to exiting the cab of the fire apparatus, describe the driver-operator's responsibilities after exiting the fire apparatus. Also, describe the driver-operator's responsibilities to make connections to the fire department sprinkler and or standpipe connection. Describe the driver-operator's role in troubleshooting problems on the scene with the fire apparatus or its equipment. Describe the driver-operator's role in the safe operation of the pump. Describe the various types of apparatus-mounted equipment found on different fire apparatus. Introduction. All fire apparatus are operated in two basic ways: in driving operations and in on-scene operations. The focus of this chapter is the on-scene operations, in which the driver-operator will play a role at the scene of an emergency. This includes operating the fire pump and other fixed systems and equipment that are mounted to the fire apparatus. While operating the fire pump, the driver-operator is responsible for producing effective hand line or master streams, engaging all pressure control and safety devices, setting the related flow for the fire attack operation, continuously monitoring the apparatus for potential problems. When operating other fixed systems and equipment, the driver-operator must follow the manufacturer instructions and department policies and procedures. These fixed systems may include any apparatus-mounted equipment. Fire pump operations. As the driver-operator, securing a water source upon arrival on scene is one of your primary responsibilities. While on the fire ground, you will operate the fire pump from one of three different water sources. Internal water tank includes the water in the apparatus-mounted water tank, has a limited amount of water, must be supplemented by other source of water before it runs out. Pressurized source includes water from a hydrant or another fire pump. Both will supply water under pressure. Most common pressurized source is the hydrant. Static source includes water sources such as a lake, stream, pool, or water tank. Water must be drawn into the fire pump using hard suction hose. This operation is covered in the chapter Drafting and Water Shuttle Operations. The driver operator must also be capable of transferring water from an internal water tank supply to an external source, a practice referred to as a changeover operation. In-cab procedures. When approaching the scene, position the fire apparatus according to your fire department's policies and procedures, and turn the front wheels toward the curb on a 45-degree angle. If the fire apparatus should then happen to move for any reason, it will travel in the direction of the curb and stop, making the scene a little safer for all involved. If no curb is present, you should still position the wheels in this manner so that the fire apparatus is not pushed straight ahead or into the other side of the street. At this point, all unnecessary emergency lighting, such as headlights, should be turned off except what is needed for the protection of personnel working in and around the fire apparatus on scene. Leaving all the emergency lighting on can drain the electrical system of the fire apparatus. Newer fire apparatus have features that automatically change emergency response lighting to on-scene modes. This is a feature that you would use when operating at the scene of an emergency. An older fire apparatus, you must explicitly choose which emergency lights remain illuminated once you have arrived on scene, but before you exit the cab of the fire apparatus, there are several steps that you need to complete. Exiting the cab prematurely can waste valuable time and cause you to overlook an important function in the cab. When you are content with the placement of the fire apparatus, place the transmission into neutral or park based on the fire apparatus. Next, apply the parking brake. Failure to apply the parking brake on today's modern fire apparatus cause an unsafe situation and prevent the pump's throttle from working, thus rendering the pump inoperable. Change the fire apparatus transmission from road position to the pump position. This will transfer the motor's power from the drivetrain to the pump, which allows the pump to operate. A pump shift control switch can be found inside the cab. It may be electronic, mechanical, or pneumatic. Place your foot on the brake and move the pump switch from the road position to the pump position. It is important to pause in the neutral position between the road and pump positions, as this allows the fork in the transfer case to correctly move from the road to the pump position. If the transfer is made too quickly, the fork may not have had enough time to move over correctly. Look for the pump engaged indicator light to ensure that this switch has actually taken place. Place the apparatus transmission into drive. This allows the motor to power the pump instead of the drivetrain of the fire apparatus. Upon proper engagement of the pump, a light near the pump shift control switch or in the cab will become illuminated. This indicates that the pump is engaged with the transmission and ready to pump. In conjunction with this OK to pump light, you should hear the revolutions per minute RPM of the fire apparatus increase slightly, and depending on the apparatus, you may see a reading of 10 to 15 mile per hour, 16 to 24 km per hour on the speedometer. Not all apparatus will show a speed increase on the speedometer. However, as some speedometers are disabled when the apparatus is in pump. For push-button transmission selectors, keep the transmission selector display to verify that the transmission is in the correct gear and that the apparatus is in fact in pump. Seeing 5 on the selector would indicate that the shift from road to pump did not occur and the apparatus is still in drive. These changes signal that the transmission is now spinning the impeller of the pump. Exiting the cab. Your first task upon exiting the cab of the fire apparatus is to check the wheels of the fire apparatus. Follow your department's standard operating procedures or guideline, SOP and SOG. as well as the manufacturer recommendations regarding which wheels are to be chocked. Usually 2 wheel chocks are placed against the rear driver's side tires. This is necessary in case the fire apparatus moves during the incident. It will be stopped by the wheel chocks. Next, circulate water into the pump. Walk to the pump panel on the fire apparatus and open the tank to pump valve. This valve allows water to flow from the onboard tank into the pump. Depending on the manufacturer of the fire apparatus, the label for this valve may use different terminology. For example, water or tank to pump. Becoming familiar with the layout of the pump panel and knowing how the valves operate will greatly enhance your efficiency in operating the pump. At this point, water is flowing into the pump, but you need to remove any air inside the centrifugal pump for it to operate properly. This small positive displacement pump draws air and water from the top of the centrifugal pump. The centrifugal pump can pump only fluids, not air. Once the pump is primed, no air inside the pump. Open the tank refill valve. This valve allows water to flow from the pump back into the onboard tank. It's basically a small discharge that directs water only back inside the onboard water tank. The label for this valve may carry any of several names such as recirculation valve or tank refill. Completing this procedure ensures that water flows from the onboard tank into the pump and then out from the pump back into the tank. This will help keep the pump from overheating. The steps for engaging the fire pump with an automatic transmission are summarized in Skill Drill 11-1. Internal water tank. Once the fire pump is engaged, the driver operator is ready to supply the attack lines for firefighting operations using the internal water tank as a water supply. This approach has the advantage of providing for a quick deployment of water, but is limited by the amount of water carried on the apparatus. Usually the internal water tank is used only to fight small fires, such as vehicle fires, dumpster fires, small brush fires, and other nuisance fires, and also to start the initial fire attack until a large water source can be obtained. If more water is necessary than the amount carried on the apparatus, then an external water supply from a pressurized water source or a static water source must be established. Pressurized sources. It is the driver operator's responsibility to secure a water source upon arrival on the scene. Fire hose evolutions are critical in the driver operator's success. Fire hose evolutions are standard methods of working with fire hose to accomplish different objectives in a variety of situations. Most fire departments set up their equipment and conduct regular training so that firefighters will be prepared to perform a set of standard hose evolutions. As part of hose evolution, specific actions are assigned to specific members of the crew depending on their riding positions on the fire apparatus. Every firefighter should know how to perform all of the standard evolutions quickly and proficiently. As the driver operator, you should know the pressures at which the lines need to be supplied and should ensure that the lines are properly flaked out before they are charged with water pressure. You need to know not only how to deploy the hose lines, but also which size, length, and nozzle configurations are required in order to supply the attack lines with the correct water flow for the extinguishment. Hose evolutions are divided into supply line operations and attack line operations. Supply line operations involve laying hose lines and making connections between a water supply source and an attack pumper. Attack line operations involve advancing hose lines from an attack pumper to apply water onto the fire. Supply line evolutions. The objective of laying a supply line is to deliver water from a hydrant or an alternative water source to the attack pumper. In most cases, this involves laying a hose line with a moving vehicle or dropping a continuous line of hose out of a bed as the fire apparatus moves forward. It can be done using either a forward lay or a reverse lay. A forward lay starts at the hydrant and proceeds towards the fire. In this case, the hose is laid in the same direction as the water flows from the hydrant to the fire. A reverse lay involves laying the hose from the fire to the hydrant. With this evolution, the hose is laid in the opposite direction to the water flow. Each fire department will determine its own preferred methods and procedures for supply line operations based on available apparatus, water supply, and regional considerations. Forward hose lay. The forward hose lay is most often used by the first arriving engine company at the scene of a fire. While en route to the fire scene, the driver-operator stops the engine at the hydrant close to the fire scene. A firefighter dismounts the fire apparatus and either wraps the hose around the hydrant or places a strap around it to secure the hose in place. The firefighter signals to the driver-operator to continue on to the fire by stating "Driver, go." The driver-operator proceeds to the fire scene no faster than 15 miles per hour, 25 kilometers per hour. At the fire scene, you disconnect the supply line from the hose bed, connect it to the pump, and call for the supply line to be charged with water. The forward hose lay allows the engine company to establish a water supply without assistance from additional company. It also places the attack pumper close to the fire, allowing access to additional hoses, tools, and equipment that are carried to the fire apparatus. A forward hose lay can be performed using medium diameter hose, 2.5 inch or 3 inch, or large diameter hose, 3.5 inch and larger. The larger the diameter of the hose, the more water that can be delivered to the attack pumper through a single supply line. When the MDH is used and the beds are arranged to lay dual lines, a company can lay 2 parallel lines from the hydrant to the fire. If the fire hydrant is close to the fire, it may supply a significant quantity of water to charge the lines, rather than using an interim supply engine to boost the flow. A 5-inch hose can supply 700 gallons per minute over a distance of 500 feet and lose only about 20 to 25 psi of pressure due to friction loss. Four-way hose hydrant valve. In situations where long supply lines are needed, or when MDH is used, it is often necessary to place a supply engine at the hydrant. This supply engine pumps water through the supply lines so as to increase the flow to the attack pumper. Some departments use a 4-way hydrant valve to connect the supply line to the hydrant. Ensures the supply line can be charged with water immediately, and still allows for the supply engine to connect to the line later. When a 4-way valve is placed on the hydrant, the water flows initially from the hydrant through the valve to the supply line, which delivers the water to the attack pumper. The second engine can hook up to the 4-way valve and restrict the flow by changing the position of the valve. At this point, the water flows from the hydrant to the supply engine. The supply engine can then increase the pressure and discharge the water into the supply line, boosting the flow of water to the attack pumper. This operation can be accomplished without uncoupling any lines or interrupting the flow. Reverse hose lay. The reverse hose lay is the opposite of a forward lay. The hose is laid out from the fire to the hydrant in the direction opposite of the flow of water. This evolution can be used when the attack pumper arrives at the fire scene without a supply line. It is also used to supply the attack pumper directly through the hydrant. The reverse hose lay may be a standard tactic in areas where significant hydrants are available and additional companies that can assist in establishing water supply will arrive quickly. In this scenario, the company is assigned to lay a supply line from the attack pumper to the hydrant. The first engine arrives on scene of the fire and begins a fire attack. When the second engine arrives at the scene, it drops off the firefighters and the fire officer. At this point, the second engine deploys the LDH supply line to the first engine, where it is connected to the engine's intake. The second engine then proceeds to the water source, laying the LDH as it drives no faster than 15 miles per hour. When this apparatus arrives at the water source, the driver operator of the second engine will be operating alone. He or she secures a water supply, connects the supply line to a LDH discharge, and pumps water to the first engine through the supply line. The attack pumper focuses on immediately attacking the fire using water from the onboard tank. The supply engine stops close to the attack pumper, and the hose is pulled from the bed of the supply engine to the intake on the attack pumper. The supply engine then drives to the hydrant, or alternative water source, and pumps water back to the attack pumper. Usually the supply engine parks in such a way that the hose can be pulled from the supply engine to the inlet to the attack pumper. Split hose lay. A split hose lay, also called an alley lay, is performed by two engine companies in situations where hoses must be laid in two different directions to establish a water supply. This evolution can be used when the attack pumper must approach a fire either along a dead-end street with no hydrant or down a long driveway. To perform a split hose lay, the attack pumper drops the end of its supply hose at the corner of the street and performs a forward lay towards the fire. Normally, the firefighter would get out of the fire apparatus and secure the supply hose to the hydrant. In this case, however, there is no hydrant in the immediate area, and the firefighter has to secure the end of the supply line to a fixed object, such as a street sign or a tree, to keep it from dragging behind the attack pumper as the apparatus drives away. When the supply engine gets to the intersection where the end of the attack pumper's supply hose is anchored, it will stop and pull off enough hose to connect to the end of the supply line, and then perform a reverse lay to the hydrant or water source. When the two lines are connected together, the supply engine can provide water to the attack pumper. A split lay often requires coordination by two-way radio, because the attack pumper must advise the supply engine of the plan and indicate where the end of the supply line is being dropped and anchored. In many cases, the attack pumper is out of sight when the supply engine arrives at the split point. The split hose lay does not necessarily require split hose beds. It can be performed with or without split beds if the necessary adapters are used. Connecting a fire department engine to a water supply. When an engine sets up at the hydrant, supply hoses must be used to deliver water from the hydrant to the engine. This special type of supply line is intended to deliver as much water as possible over a short distance. In most cases, a soft suction hose is used to connect directly to the hydrant. Alternatively, the connection can be made with hard suction hose or with a short length of large diameter supply hose. Securing a water source. As the driver operator, securing a water source upon your crew's arrival on the scene is one of your primary responsibilities. Before you even leave the fire station to respond to the scene, you should have a working knowledge of water sources at or close to the scene. This can be accomplished by using a map book with hydrant locations in it, or by being familiar with water sources within the response area, including lakes, ponds, canals, and drafting hydrants. Upon your arrival on the scene, it is generally the fire officer's call whether you will lay a supply line to the incident. If the fire officer calls for a supply line, follow your fire department's SOP for laying this line. If your crew is the first engine company on scene, the fire officer may forego laying a supply line and proceed straight to the scene. This tactic is commonly used when the second due engine is immediately behind the first due engine. Use of this tactic should be communicated by the officers on both engines so that the water supply is secured regardless of the order in which units arrive on scene. Sometimes an available hydrant may be located in close proximity to the building on fire. In such a case, you may position the fire apparatus so that you can use a section of hose to be connected to the hydrant instead of performing a forward lay. In this kind of hand lay, you position the engine close to the fire scene and deploy the supply hose from the bed of the fire apparatus to the hydrant, either yourself or with very little assistance from other firefighters. Hand lays. If you find yourself having to create a hand lay to a hydrant, several considerations must be taken into account. What is the distance between the fire apparatus and the closest hydrant? What is the best hydrant to make the connection? How long will this step take to complete? To determine how far away the closest hydrant is, either reference the map book in your fire apparatus or simply eyeball the estimated distance from your pump intake to the hydrant. When determining the best hose to make the connection, you may or may not have several options for hoses. Suppose the hydrant is approximately 15 feet away. If you use LDH in your fire department, it is common practice to carry short lengths of LDH for the purpose of making a connection between the fire apparatus intake and the hydrant. These lengths of hose generally range from 15 feet to 25 feet and have names such as soft suction hose or pony lines. It is important for you to know how long each line found on the fire apparatus is and how many of these lines the fire apparatus carries. This can be accomplished during your morning checkout of the fire apparatus by removing the hose and laying it out for inspection. Some fire departments may carry reduced length 3-inch or 2.5-inch hose for refilling the onboard tank from the hydrant. Use caution when applying hose lines with these diameters as supply lines during fire operations. You may find that you need to pump more water than these lines can deliver. If the hydrant is 60 feet away, use the shorter LDH lines. Most likely will not be an option. In most cases, pulling hose from the hose bed is the next choice. If you carry LDH, it is most often available in 100-foot lengths. You need to pull a full section of the hose from the hose bed and deploy it between the fire apparatus and the hydrant. Keep in mind the direction in which you need to go. Your goal is to minimize sharp turns, twists in the hose, thereby reducing kinks and severe bends that might reduce the flow. Watch out for any oncoming traffic while operating in the roadway. Always wear your traffic safety vest as required by your department. When considering the third question, how long will this hand lay take to accomplish? You must take into account several factors. The distance from the fire apparatus to the hydrant, the choice of hose, any possible obstacles in the way to deploy the hose, such as vehicles, trees, or bushes. An additional consideration when obtaining a water source is the need to double tap a hydrant. When connecting to a dry barrel hydrant during a hose lay or connecting straight to the hydrant, fire departments often use the largest connection. This leaves 2.5-inch port connections unused. Once the hydrant is open, however, these additional connections cannot be subsequently used unless the hydrant is shut down, thereby cutting off the water supply at least momentarily. The hydrant is capable of delivering additional water through these port connections. If you anticipate that additional water may be needed, place an appliance such as a gated ball valve on the dry barrel hydrant prior to opening the hydrant. If additional water is needed, a supply line can be connected from the valve to the intake of the fire apparatus. Always follow your local SOP when obtaining a water supply. Only with practice will you build confidence and become more proficient in securing a water source. Follow the steps in Skill Drill 11-2. Connecting supplies, hose lines to standpipe and sprinkler. Another water supply evolution is furnishing water to a standpipe and sprinkler systems. Fire department connections, FDCs, on buildings are provided so that the fire department can pump water into the standpipe and/or sprinkler systems. This setup is considered to be a supply line because it supplies water to the standpipe and sprinkler systems. Such a supply line is connected to the discharge side of the attack pumper. The function of the hose line in this case, is to provide either a primary or secondary water supply for the sprinkler or standpipe system. The same basic techniques are used to connect the hose lines to either type of system. Standpipe systems are used to provide a water supply for attack lines that will be operated inside a building. Outlets are provided inside the building where the firefighters can connect attack lines. The firefighters inside the building must then depend on firefighters outside the building to supply the water to the FDC. Two general types of sprinkler systems exist. A dry standpipe system depends on the fire department to provide all of the water. A wet standpipe system has a built-in water supply, but the FDC is provided to deliver a higher flow or to boost the pressure. The pressure requirements for standpipe systems depend on the height at which the water will be used inside the building. The fire department connection for a sprinkler system is also used to supplement the normal water supply. The required pressures and flows for different types of sprinkler systems can vary significantly. Unless more specific information is available, sprinkler systems should generally be fed at a pressure of 150 psi. Due to certain building characteristics within a response area as well as the height and construction materials used in the building, private fire protection systems may be present in a fire building. As a driver operator, it is your responsibility to have a complete and thorough understanding of these systems. Pre-incident planning as well as familiarization with your response area will help you to identify these buildings that have sprinkler systems and standpipes. When performing this planning or during routine driving through your response area, you should be looking for the FDC's hydrant locations and sprinkler valves associated with the building. If you are unaware of the locations or cannot find the FDC connection on the scene, you become the owner of the problem, with all eyes looking at you for its resolution. The fire department connection can be either freestanding or wall-mounted. It generally consists of a Siamese connection with two 2.5-inch female connections. Depending on the occupancy, multiple connection standpipes may be present. Local codes may dictate the number and size of standpipes provided. Each female connection should have a clapper valve inside the Siamese connection that will swing to the closed position on the connection that is not in use. This allows one side of the Siamese connection to be charged without water discharging from the other open intake. Depending on the fire department's SOPs, it is generally recommended that both or all connections to the FDC be used when supplying a standpipe. If the exterior FDC connection is damaged such that a connection to it is impossible, an accepted practice is to hook up to the standpipe discharge on the first floor of the building. This may allow you to connect only one line into the standpipe, but better one line than none at all. After the engine is connected to the standpipe sprinkler, the fire department's SOP/SOG may specify when you will supply the standpipe. One factor that may affect this decision is whether the standpipe is wet or dry system. Whether a system is wet or dry may be dictated by state or local codes. A wet system has water under pressure in the pipe at all times. It is typically supplied by the water utility department having jurisdiction. A dry system has no water in the pipe and depends on the fire department to supply the water. Regardless of which system may be present, a supply line must be established. Follow the steps in Skill Drill 11-3 to connect hose to the fire department connection. Figure 11-13 and 11-14 show examples of fire department connections and standpipe connections, a freestanding FDC and a wall-mounted FDC. Performing a changeover. When you first arrive at the scene, you may initially need to supply attack lines from your onboard tank and then have a supply line laid to your pump from another fire apparatus or a hand-laid supply line. When supplying attack lines from the onboard water tank, you are limited by the amount of water in the tank. The tank water will last only so long, so a supply line will be needed to sustain a fire attack for longer periods. It is wise to recognize early on that the amount of water flowing through the attack lines is or will be far greater than the amount of water carried in the onboard tank. For this reason, it is important to establish a supply line early and to perform a changeover operation. During a changeover operation, you switch from the onboard water tank supply to an external water source. The goal with this tank is simple: to make the changeover prior to running out of water in the tank with the least amount of pressure fluctuation for the firefighting crew on the nozzle. Overpressurizing the attack lines can cause firefighters to lose control of the hand lines, causing an unsafe situation. As the driver-operator, you need to constantly supply the attack lines with the correct pressure to ensure a safe operation. Two devices that will assist you in this task are the pressure relief valve and the pressure governor. In a multi-stage pump, you may also need to use the transfer valve. Figure 11-17 shows a pressure relief valve. Figure 11-18 shows a pressure governor, and Figure 11-19 shows a transfer valve. There are several factors you need to keep in mind prior to the changeover. How much water is currently in the tank? What are the flow rate, GPM, and pressure, PSI, currently used on the attack line by the firefighting crew? What is the incoming pressure from the supply line? What is the setting of the pressure control device? At the beginning of the changeover, keep your eyes on the pressure gauge for the line that the attack crew is using. The goal is to ensure that fluctuation does not exceed 10 psi. Slowly open the valve from the external water source, which will introduce water into the pump. Once this valve has been fully opened, close the tank to pump valve. The tank to pump valve does not need to be closed on the newer apparatus. A check valve will close so as to not allow water to flow into the pump from the tank once the supply line intake is opened. Many departments leave the tank to pump valve open as an extra safety feature so that the tank water will automatically flow into the pump if the pressurized supply is lost and the driver operator is remote from the pump panel for some reason. If the pressure relieving device is set for a lower pressure than the incoming supply pressure, you will need to increase the setting on the valve above the incoming pressure from the supply line. Once the changeover has been accomplished, recheck the gauges to ensure that they have the proper settings. If no other additional lines are required for pumping, now is a good time to refill the onboard tank. Slowly open the tank fill valve to allow water to refill the tank. The tank fill valve should be open just enough to let water into the tank, but not enough to permit fluctuations of pressure for the attack lines. Follow the steps in Skill Drill 11-4 to perform a changeover operation. Always refer to and follow the manufacturer's recommendations for your department-specific apparatus. Monitor the fire pump. As the driver-operator, you have additional duties and responsibilities on scene aside from pumping water or foam. Once the pumping operation is underway, you must monitor specific gauges on the pump panel, such as the oil pressure and engine temperature. During the pumping operation, if you discover that the engine temperature is increasing, you need to take steps to reduce this temperature. First, shut down or turn off all unnecessary loads on the engine, such as the air conditioning system and external lighting. Next, if needed, open the auxiliary cooler on the fire apparatus. The auxiliary cooler is a heat exchanger system usually installed in the engine radiator hose. The heat exchanger allows the engine coolant to flow around the copper piping in the tube. The copper piping, which has cold pump water from the fire pump flowing through it, reduces the temperature of the engine coolant by conduction in the heat exchanger. In old apparatus, sometimes simply opening the cab and lifting the engine cover to allow more air to get to the engine will keep the engine cool. Modern diesel engines, however, are designed to get air to the engine with engine covers in the closed position. Opening the engine covers in diesel engines will change the airflow and could negatively affect the operation of the engine significantly. Follow the steps in Skill Drill 11-5 to operate the auxiliary cooling system. Your final duty as driver-operator on the Fireground is to disengage the fire pump. Follow the steps in Skill Drill 11-6 to disengage the fire pump with an automatic transmission. Always refer to and follow the manufacturer's recommendations for your department-specific apparatus. Reduce the throttle to idle speed. Operating other fixed systems and equipment. Upon arrival at the emergency scene, the driver-operator will position the apparatus for effective operations. The chapter Emergency Vehicle Driving covers the procedure for placing the apparatus at an incident. Each apparatus will be equipped with a unique complement of tools and equipment according to its specific function on the emergency scene. The apparatus driver is responsible for knowing how to operate every piece of equipment his or her apparatus. While most of the time other members of the company may be the ones using the equipment, the driver will support them by preparing it for use and inspecting it before the shift begins. When positioned at the scene of an incident and operating the emergency lights and or other electrical appliances, it is advised to engage the high idle switch, which sets the apparatus engine to 900 to 1100 RPMs. High idle will typically be disabled when the apparatus is in pump. This step will help ensure that the alternator is providing its full amperage rating. National Fire Protection Association, NFPA 1901 Automotive fire apparatus requires that the vehicle's electrical system be monitored by an automatic load management system, which is designed to protect the electrical system from needless damage while maintaining the operation of essential devices. Damage to the apparatus electrical system can occur if the total continuous electrical load exceeds the minimum continuous electrical output. Many new fire apparatus have complex electrical systems, whose outputs will exceed the alternator capacity and can be supplied only by the deep discharge of the apparatus batteries. These high-powered batteries experience serious damage when they are deeply discharged. The automatic load management system, therefore, is designed to protect the electrical system from needless damage while maintaining the operation of essential devices. A system that is protected with an automatic load management system incorporates a load sensor, which is a component that will evaluate electrical load in a specific order to prevent overloading the electrical system. The electrical system also has a load monitor, a component designed to prevent any additional electrical loads from exceeding the fire system's capabilities. In these circumstances, the system will perform load shedding, in which a component deactivates unnecessary electrical loads in order of necessity and to prevent damage to the system. The driver-operator must anticipate how the automatic load management system works and learn how to operate it correctly. It is especially important to recognize the difference between load shedding and a possible electrical system failure. Apparatus-mounted equipment. Fire apparatus are equipped with a variety of apparatus-mounted equipment. This equipment is not specific to every type of apparatus or fire department. The driver-operator is responsible for its maintenance and safe operation. While each apparatus manufacturer provides different systems and equipment on its apparatus, they all share some common features. The driver-operator should reference the owner's manual to obtain more information about this apparatus-mounted equipment. Electric generators. The fire apparatus driver-operator should not assume that a dependable supply of electrical power will be provided at every emergency scene. Some emergencies may occur in isolated areas that lack power sources, or the involved structure itself may be unable to supply electrical requirements of the fire department. It is prudent for the fire apparatus to be self-sufficient and provide its own electrical power, generally 110-volt alternating current, delivered through electrical cords. This portable electricity can be supplied by a generator, an engine-powered device that creates electricity, or an inverter, an appliance that converts 12-volt direct current from the vehicle's electric system to 110-volt AC power. An inverter can provide a limited amount of AC current and is typically used to power only a small electric tool or a few small lights. It does not produce enough power to operate the high-powered lights that are usually used to illuminate an emergency scene. Drawing too much current from an inverter can seriously damage it and other electrical components on the apparatus. Given the limitations of inverters, the most common power source for fire apparatus is the generator. Three types of generators are found on the fire apparatus. Portable generator, the smallest of the three options, usually powered with gasoline fuel. Although it does not offer the high output of the other two types of generators, it makes up for its shortcomings with its light weight and portability. It can produce up to 6,000 watts of power and come in a variety of sizes. Apparatus-mounted generator. Permanently mounted on the apparatus, has a motor separate from the vehicles that drives it, may be powered by gasoline or diesel fuel, may use the same fuel tank, which is usually diesel fuel, as the apparatus, or it may have its own fuel supply. Transmission-driven generator. Powered by the vehicle's motor and is driven by a power takeoff PTO system. The apparatus engine powers the generator and other system that is converted to its driveline. May produce 25 kilowatts or more. To engage a generator PTO, follow the steps in Skill Drill 11-7. To disengage a generator PTO, follow the steps in Skill Drill 11-8. Scene lighting equipment. Lighting is required to illuminate the night emergency scene and enable safe, efficient operations. It is usually the responsibility of the driver-operator to provide for sufficient scene lighting while other members of the crew are completing tasks at the incident. Departmental SOPs or the incident commander IC will dictate responsibilities or the setting up of lighting. Fire apparatus are equipped with a vast assortment of lighting equipment. Some fire departments equip all of their apparatus with the same type of lights that are found in the same location on the apparatus. Other departments may have special apparatus respond to the incident to provide on-scene lighting. Almost all fire apparatus have some capability to illuminate areas around the apparatus. The ability to adequately light up an emergency scene may mean the difference between a safe emergency scene and a dangerous one. Some lights have a different pattern than others. For example, spotlights project a narrow, concentrated beam of light, where floodlights project a more diffuse light over a wide area. When used incorrectly, these lights may also create a problem. If they are directed improperly at the scene, they can temporarily blind firefighters or approaching vehicles. The scene lighting should be proficient, with lights positioned above and behind the firefighters to lessen the chance of any problems. 4 types of lighting equipment may be found on the fire apparatus. Lanterns project a powerful beam of light and are easily maneuvered on any emergency scene. Can be equipped with a shoulder strap for easy transportation, may be set up inside a structure to illuminate the work area after the fire is under control, or used during the initial stages of vehicle extraction. With the visibility provided by this powerful light, the firefighters can begin their operation while other more powerful lights are set up. Powered by a rechargeable battery that has a recharging station located on the apparatus. When the apparatus engine is operating, the battery is recharging for the next use. May provide lights ranging from an 8-watt spotlight to a 20-watt flood beam. Portable lights. Powered by a generator and supplied by an electrical cord. Some are mounted on tripods and can be deployed at various heights. Can be taken into buildings to illuminate the interior or set up outside to light up emergency scenes. Usually range from 300 to 1500 watts. Can use several types of bulbs, including quartz and halogen bulbs. Apparatus-mounted lights. Floodlights or spotlights may be attached to the exterior of the apparatus. Some are mounted to the body of the apparatus and controlled by a single switch inside the cap. Provide a quick and efficient way to illuminate one side of the work area. When used, they should completely illuminate the seam and eliminate dark shadows. To operate them, the driver-operator must first engage the generator and then control the individual switches for each light at the sides and rear of the apparatus. Do not preset all of the individual light switches to the on position. Turning on all of them simultaneously may place an unnecessary load on the generator and seriously damage it. Some lights may be angled slightly toward the ground to provide better coverage of the emergency scene. Other types of lights are attached to a pole and elevated from different locations on the apparatus. Figure 11-27. These lights may be manually raised from their nested position to better illuminate the emergency scene. Many newer apparatus use LED scene lights that run off the vehicle's 12-volt system and do not require generator power. Tower lights may be more appropriate when the body-mounted lights are insufficient to meet the incident lighting requirements. Can be operated above most obstacles and provide the desired scene lighting. May be controlled from the ground with a remote control or a control panel in a compartment. Raised from the top of the apparatus by either a 12-volt motor or a pneumatic power system. Lights extend height above the apparatus is usually not more than 15 feet. Multiple 1500-watt halogen lamps, or LEDs, on the newer tower lights are usually mounted at the top and may provide a 360-degree rotation with tilt capabilities. Also illuminated by a 12-volt light to signal to the drivers that they are in the raised position. Some apparatuses are also equipped with sensors to notify driver-operator when the tower light is still in the raised position, a factor that must be taken into account when the apparatus is moved. Power equipment distribution. The power needed to operate the electrical equipment must be supplied through the electrical cable or cord. This cord must be waterproof and provide a durable insulation. The cord that is used in everyday household appliance applications is not suitable for the Fireground. Always purchase quality commercial-grade electrical cords and adapters for fire surf use. Most electrical cords will have 3-prong adapter. The most common size of electrical cord is 12-gauge 3-wire type. The size cord works well for most 110-volt powered equipment and is usually stored on the apparatus in lengths of 50 to 100. For normal operations, these lengths are adequate for operations close to the fire apparatus. When multiple cords are necessary, a junction box may be used. A junction box is a device that attaches to the electrical cord to provide additional outlets. It allows several cords to be, or powered operated tools to be supplied by a single electrical cord that may be used as a mobile power outlet. In this case, a single cord is stretched from the apparatus, a junction box is attached at the end, and the other cords or tools are then connected to the junction box. A small light is attached to the top of the junction box to ensure it has power and the crew can locate it in the dark. This light turns on only when the junction box is charged with electricity. The junction box must be waterproof but be durable and have flip-up covers lined with soft neoprene rubber attached outlet openings. When electrical equipment is required at a location that is considered considerable distance from the apparatus, or if the equipment operates on 220 volts, a larger cord is needed. For these situations, most departments equip their apparatus with an electrical cord reel. Electrical reels are usually powered by a 12-volt DC rewind motor. The reel holds up to 100 to 200 feet of electrical cord and is sized to the load and circuit breaker rating. Using too small of a cord for a high electrical flow may overload the cord and cause it to overheat. The connectors and plugs used for fire department mechanical electrical equipment may have special connectors that attach with a slight clockwise twist. This feature keeps the power cord from becoming unplugged during fire department operations. Powered rescue tools. NFPA 1936 Powered Rescue Tools defines the following components that relate to this section of the chapter. Power rescue tool is a tool that receives power from the power unit component and generates energy used to perform one or more of the following functions: spreading, lifting, holding, crushing, pulling, or cutting. These tools are generally powered by a power unit, which is a prime mover and principal power output device used to power the rescue tool. Power units rely on either a portable power unit or a PTO-driven system on the fire apparatus. The power rescue tool system generally consists of a reservoir, fluid, a power unit, an enclosed system, and an agitator used to operate a power rescue tool. A hydraulic reservoir is the container that stores the hydraulic fluid until it is needed in the system. It may be equipped with a filter to condition the fluid as it returns through the system. The fluid used in the hydraulic rescue tool can be phosphate ester, ethylene glycol, automatic transmission fluid oil, or a mineral-based hydraulic oil. Mineral-based hydraulic oil is most common. Each manufacturer may identify a specific type of hydraulic fluid that should be used in its product. Always reference the owner manual to determine which fluid to use. The power units for power rescue tools are usually machine powered. Manual units are still available, but this operation is usually limited to an emergency backup role. The two types of power units are described here. Portable power units, powered by an independent motor and may be transported away from the apparatus. Each unit can weigh anywhere from 26 to 97 pounds and is usually carried by one or two firefighters. Can be powered by 120 or 220 volt AC electric, gasoline, diesel, or manual hand pump, which provides emergency backup power. Gasoline and diesel units may sustain operations for only 20 to 60 minutes. Driver operators must be constantly aware of the fluid levels in these types of units. Some newer portable power units are powerful enough to allow for up to 4 tools to be operated at the same time, thereby enabling firefighters to work on several vehicles or several areas of a single vehicle at the same time. Other units will operate only a single tool at a time. PTO-driven hydraulic unit. Most powerful than most portable power units, powered by the vehicle's engine through a PTO system and activated either by remote controls or by controls mounted inside the vehicle's cab. Apparatus engine usually must sustain a set RPM to achieve the hydraulic pump required RPM. In most cases, the engine must operate in high idle position to meet this demand. Some are capable of operating up to 6 tools simultaneously. Driver operator must be aware of the limitations of the equipment on his or her apparatus. Do not attach and operate more tools than the manufacturer recommends, as this may damage the equipment and delay the response operation. A positive displacement pump is used to pressurize the hydraulic fluid in the system. This pump may be either a single-stage or two-stage model. A single-stage pump pumps a constant pressure of flow of fluid. A two-stage pump operates at 2 different pressure modes. Depending on the apparatus, the system first operates in a low-pressure, high-volume mode, 5,000 psi, until the tool is under a load. Then the system pressure builds, and the second mode, a high-pressure, low-volume mode, 10,000 psi, is activated to deliver added power. Sometimes this switching of modes can cause a few seconds delay in the unit's operation. During this gap, the operator must hold the load position until the second mode kicks in and the fluid pressure builds in the system. During the operation of tools, the pressurized hydraulic fluid will move from one section of the system to the other through the hydraulic hose lines, pressurizing the system, and then returning to the hydraulic fluid reservoir. Hydraulic hose lines are usually kink-resistant and electrically non-conductive. They are constructed with several reinforced layers of thermoplastic or rubber material. The method used to couple the hose lines will differ depending on the manufacturer. Driver operators should familiarize themselves with the correct method for coupling and uncoupling hydraulic hose lines for their department equipment. Once the fluid is under pressure and traveling through the system, it operates as an actuator. An actuator converts the fluid pressure in the hydraulic rescue tool system into a mechanical force. This force is then used to operate one of four types of hydraulic tools. A spreader, shown in figure 11-31, power rescue tool that has at least one movable arm that opens to move material. Contains a single piston that connects two movable metal arms. Cutter, shown in figure 11-32, has at least one movable blade that is used to cut, shear, or sever metal. Design of this tool means that it is intended solely for cutting. Combination tool, capable of at least spreading and cutting. Extension ram has a piston or other type of extender that generates extending forces or both extending and retracting forces. Uses the most hydraulic fluid during operation, so the pump being used must have enough capacity to allow the ram to reach full extension. During extension, this is a very powerful tool. During retraction, it can produce only approximately half of its full operating force. These tools are extremely powerful and should be used only by firefighters who are properly trained in their operations. Always reference the manufacturer operator's manuals before use. To engage a PTO-driven hydraulic system, follow the steps in Skill Drill 11-9. To disengage a PTO-driven hydraulic system, follow the steps in Skill Drill 11-10. Summary. As the driver operator, securing water source upon arrival at the scene is one of your primary responsibilities. Potential water sources include the internal water tank, a pressurized source, and a static source. Before you leave the fire station to respond to the scene, you should have a working knowledge of water sources at or close to the scene. This can be accomplished by using a map book with hydrant locations in it and becoming familiar with water sources within the response area, including lakes, ponds, canals, and drafting hydrants. When your crew first arrives at the scene, you may initially need to supply attack lines from your onboard tank, but then have a supply line laid to your pump from another fire apparatus or via a hand-line supply line. Once the pumping operation is underway, you must monitor specific gauges on the pump panel to ensure that the adequate supply of water or foam is available for the duration of the incident. Fixed apparatus systems include generators to power lights and equipment. Hydraulic systems may be powered by the apparatus or a separate power unit. Okay, class, this concludes the lecture on Chapter 11, Fireground Operations. If you have any questions or concerns, please contact your instructor, and I'll see you in the next chapter.